All right, this is part 2 for 7.5 when we're solving trig equations. I want to talk about a few more strategies and some things that can happen and also how we write our answers, looking at what are the possibilities when you solve an equation to find that value that makes it true. We have lots of different things that can happen. Sometimes equations don't have any solutions at all. Sometimes they have multiple. We want to talk that through. So make sure you have your pink sheet handy, your formula sheet there, so you're ready to do some of those substitutions. All right, so yesterday we were just kind of finishing up with talking about things to check for when you're solving. So things you need to make sure you look for. So one thing we talked about was functions. Make sure you check for the functions being the same. Another thing we talked about is check your angles. Make sure that your angles are the same. So when we take a look at this first one, we have sine squared of x and cosine squared of x. Well, the function names are different. One is sine, one is cosine, but the angles are okay. They're both x. But we're still going to have to try to think a little bit about, well, how are we going to solve this if the functions are different? And if they are different, our kind of conclusion I think we came to yesterday is we might have to make a substitution then. So we might have to substitute to make them the same. Now let's just think common sense about this equation first. We have sine and cosine squared being equal. Is it possible in the unit circle for sine and cosine to be the same? Well, sure, it can happen. That's at the 45-degree angle. So it seems to me like this could be something that would definitely have solutions when these things are equal to one another. But in this situation, if I'm actually going to algebraically figure out what those values are, I'm going to have to make a substitution. So take a look at the pink sheet and look and see if there's anything you can substitute for either one of those. And if you look way up at the top on the Pythagorean, I can substitute in 1 minus cosine squared for sine squared of x. That's one possibility. Another choice would be you could put in, and this is just another possibility, you could have done 1 minus sine squared of x for the cosine squared of x. And that works great too. It doesn't matter. You can do it either way. Those are under the Pythagorean identities. And then now we have everything in cosine and in x. Okay, well let's take a look at where we could go from there then. If you write it as an algebra thing, it would look like this. 1 minus x squared equals x squared as an algebraic, just straight up algebra equation. So you have like terms. They're both x and they're both to the second power. If you're thinking like, okay, let's get all of our terms on one side, let's move those x squared terms together. So if you're thinking of it just as an algebra thing, it would look like this. We'd add the x squared. Then now to solve for the x squared, I would divide by 2. So I have x squared equals 1/2. And then to undo squaring, I would square root. And remember, when you square root, you get two answers, right? Plus or minus, two possible answers. So I'm going to get x equals plus or minus square root of 1/2. Now that may not look very nice right now, but square root of 1 is 1 over square root of 2, and if you rationalize, you get your square root of 2 over 2. So it is really actually not that bad. It comes out to be a really nice number for trig anyway. So let's take a look and do that back for this trig equation. So remember, if there's something that doesn't make sense or you get stuck in the trig, rewrite it as an algebra. So I'm going to go ahead and add the cosine squared over to the other side. I'm going to divide by 2. So I get cosine squared equals 1/2. And then I'm going to take the square root on each side. So we get cosine of x equals plus or minus the square root of 2 over 2. So now I'm asking the question for what angle measurements is cosine, either positive or negative square root of 2. And I'm going to refer you back to your domain here that we're looking in, 0 to 360. So when is cosine either positive or negative square root of 2 over 2? Well, 45. Quadrant 2 would be 135. Quadrant 3 would be 225, and then quadrant 4 would be 315. It actually works out really well because when it's plus or minus, because you just need all of them, right? Every one of those reference angle places. So when we're solving, we're looking for the values that make it true. So here's one where the angles were the same, but the functions were different, so we substituted. All right, so let's try another one. Same kind of question. So check your functions and your angles. So the functions are both cosecant, kind of scary, not our normal trig functions, and just reciprocal, but the angles are the same, so they're both x, so that's good. So the functions and the angle measurements are good. So let's take a look from the algebra perspective. What do we got going on here? So I'll rewrite it as an algebra thing. So basically that's what we've got, what I just wrote in blue. I'm just trading out the cosecant function just to say why. It's degree 2. And because it's degree 2, what do we know about degree 2 equations? Well, we try to solve them by factoring if we can, right? So anytime we have a degree 2 equation, we try to see if it's factorable. So in that case, we'd pull out a y. That means in this case, we do have a GCF. It's cosecant. So when we factor, one thing to look for is a GCF. if I can write correctly here. So we look for that GCF, pull it out front. Now what that's going to allow us to do is have our two factors that we can set equal to 0, and we can solve. All right, so I set them each equal to 0 and solve. Now, when you think about what you're doing here, you're trying to see what values make this true, if any. And so if I'm going to solve these, I don't memorize cosecants. I really need to think of the reciprocal and rewrite those sentences as their reciprocals, one that I'm more familiar with. So the reciprocal for cosecant is sine. So I'm going to rewrite these as sine sentences. So if the cosecant is 0, that means sine of x would have to be 0 over, or 1 over 0 if I flip. So 1 over 0. Now, is sine ever undefined? That's what 0 or 1 over 0 would be. Is that possible? Well, no. The domain for sine is all real numbers. There's no breaks in the graph. There's no excluded values. That is physically impossible for that to happen. Think about what that would mean for your triangle, that sine is opposite over hypotenuse. Is it possible that you can have a hypotenuse of a triangle that's 0? Well, no, it wouldn't be a triangle at all then. So that's a situation where that's not possible. We can't draw that picture. So there's no solution, which is completely legitimate in an equation. Not every equation has a solution. All right, so let's talk about the other factors. So let's take a look at this one. Rewrite it as a sine sentence. So that would be sine is equal to the reciprocal, so 4 over 3. All right, well, that's not a special value ratio. Clearly, that's not something that we recognize. So try it on your calculator. Do you remember how to find x if we have sine of x? Well, we have to do the inverse, right? So if you type in inverse sine of 4/3, see what it says. All right, and I'm thinking you probably got something that said error domain, which means that is physically impossible for you entering into your calculator, which would tell me that I can't solve that equation. Now let's take a look back at this opposite over hypotenuse idea again. If this were to be a ratio in a triangle that makes sense, that means the side opposite the angle would be 4 and the hypotenuse would be 3. Is it possible for the hypotenuse to be shorter than one of the sides? Well, of course not. That's not going to happen. So this would be a no solution situation. So actually this equation, neither side of it has a solution. So neither one of these are solutions to the equation because neither one of them have values that make it true, and that's okay. Sometimes one of the factors will work and the other one doesn't. Sometimes they both work. Sometimes neither work. So this is a great example of something that has no solution. Okay, we're going to kind of transform now into how are some of the different ways that we could write our answers. Because remember, again, we have to limit our domain so we can see how many solutions that we maybe want to have. So if it's not limited, how does that change how we express our answers, our solutions? So if it's unrestricted and we're finding all values, that means we're going to have infinitely many, all those coterminal values that we talked about before. All right, so let's take a look at the next one. We're going to solve it the same way. We're just talking about how we're going to express our answers then. All right, so this one, again, think about the two things we ask. Are the function names the same? Well, yep, they're both cosine, so that's good. Are the angles the same? Well, no, they're not. One's a 2x, the other one's an x. So focus in on those angle measurements as well. What that tells me is because they're not the same, I'm going to have to substitute to try to make these the same so I can solve. I can't put like terms together if they're not alike. All right, so which one would you substitute for? Look on your pink sheet. The only thing you can put in for cosine of regular old x is 1 over secant. Not super helpful. So I'm guessing you're going to focus in on this. You have 3 different options on your formula sheet for cosine of 2x. It's always easier if they're just one, but you have 3 different options. So what would be the best thing to use? I am guessing that that's probably the one that you came up with because you want something that uses the same function. So pick the one that already has the cosine in it as well. So now we can get back to our algebra. Once that we have our function names the same, then we can go through and we can actually do our solving. So our function names are the same. They're both cosine. Our angles are the same. They're both x. What you really have is this equation right here. So if you think in algebra world, how would you solve that? Well, it's degree 2. And if it's degree 2, that usually tells us that we have to factor. Is that equation set up nicely for you to factor, though? Well, no, not really, because you always want it equal to what if you're going to factor? 0. So let's go ahead and move that cosine term over. and then we're going to factor. Now this one doesn't have a GCF. I can't pull anything out of all three terms because I have a constant. That means it's a trinomial. It's going to factor into two binomials. This is where you have to think back to your advanced algebra stuff and try to see what pairs would multiply to what we have. So to get a 2 cosine squared, only one option. 2 cosine times cosine. My last term is a -1. That means my last position numbers have to multiply to a -1. There's only one option for that. It has to be a 1 times 1. One of them is going to be positive, one's going to be negative. And I think we want it like this. Remember to check. You check your outsides plus your insides to see that they add to the coefficient in the middle. So the outsides would give us -2. Insides gives you a +1. That adds to that -1 that we want. So you need to check. It's not like you can just put the numbers wherever you want. They have to make that trinomial. So if you do the distributive property, you should get back to the original. So now that we have our factors, we can set them equal to 0 and solve. So when is cosine equal to 1 and when is cosine equal to -1/2? All right, so now this is all values. So we're still going to start the same way. Think about those reference angles. When is cosine -1/2? Well, that's a 60-degree reference angle, and cosine is negative in quadrant 2 and quadrant 3. So that means it would be 120 and 240. Now, if this was restricted to 0 to 360, I'd be done. But they said all values. So everything that's coterminal with each of those is also going to be a solution. Think about the graph. It continues infinitely in both directions. Those would be all the x-intercepts. So it's going to be crossing the x-axis at all of those places. So all of them would be solutions. Same thing on the other part here. When is cosine 1? Well, that happens at 0, but again, I need everything that's coterminal. Now, another way that people like to write that one is you could really say just 360k, because k includes 0. It's an integer, so you can just include it as one sentence. Some people like to just do the angle plus 360k, and that's fine. So the difference in how you write your answer is really pretty minimal, but it accounts for infinitely many solutions. That plus 360k tells us all possibles. So again, this was a degree 2. We solve by factoring. All right, so let's take a look at a couple more here of these principal or unrestricted ones. This one, again, same question we ask. Function names, angles. See what you think. So are the function names all the same? Well, no, because you have sine and cosine. But are the angle measurements the same? Yep, they're all of them x, right? So x, x, x. So our angles are okay, but the function names aren't. So if you think, oh, let's try to substitute, kind of tricky on this one because sine and cosine, there's really not a whole lot you can do, right? 1 over secant, 1 over cosecant, that's not really helpful. So substitution really isn't the answer for us here, although it's a great thing to think of. So I'm going to try another strategy I did with you before. I'm going to rewrite this as an algebra thing to see if you can see maybe a little bit easier what you should do. And it's a great strategy we used back when we were verifying and simplifying. If you're not sure and everything's in sine and cosine already and you get stuck, so we've talked about this lots, try rewriting it and see what you do. If you were doing that green sentence, what would you probably do in algebra? Well, you'd probably pull out a y, right? You do your GCF, and that's exactly what you're going to do here. You're going to pull out the GCF, which happens to be sine of x. Now, I know your two factors that you get don't use the same function, but we don't really care. We're just going to set them equal to 0 and solve anyway. So I can set those both equal to 0 and solve. So even though the function names are different, I still ended up with two factors. I had a GCF, so pull it out. So when is sine 0 and when is cosine equal to -1? Okay, so let's start with when is sine 0. This is all values again, so infinitely many. So sine is 0 at 0, and sine is also 0 at 180, and both of those would have to have all of the things that are coterminal with it as well. So 0 plus 360k, and then 180 plus 360k, because remember we're doing all values, all the places. Now some people would take both of those sentences and combine them into one and say this. 0, I should probably start with the 0 first, plus 180k, because these are happening every 180 degrees around the unit circle. So if you think about your picture, you start at 0, and then 180 would be here. That's 180 later, and then 360, 180 later, and so on. So some people like to combine those two sentences into one. You don't have to, but you sure can. And again, just like in our other example, you could just say 180k again, because 0 is an integer. All right, so that's one half of it. So we have either way that you want to write that. On the other side here, when is cosine equal to -1? Well, by coincidence, cosine is -1 at 180, and then plus 360k, because it would be everything that's coterminal. But are these answers already included in that? All the multiples of 180? Well, sure they are. So you can write them as two separate things. You can still include this one and the other one. You can do both. Some people just write it as a single sentence, though, because they are the same values. There's some overlap. So different parts of an equation, different factors, can have the same solutions. You know that from doing, say, parabolas. Those double roots. You can have the same answers for both pieces, or both parts. Pieces. Yeah, great word. So you can definitely have that happening, that overlap. So all values means you have infinitely many. All right, so let's try one more all values question. So I'm going to kind of box this out so you can actually see the equation. So ask yourself those questions again. Do you have the same function name? Sure you do. They're both secants. Do you have the same angle? Yep, they're both x's. So I don't really need to substitute on this one. I don't have the need for it because everything's already in the same variable with the same angle. So what you really have is this sentence right here. And if this is helpful to you, just replace your function with just an x or a y, something so you can see. You have a degree 2 equation. And how do we solve degree 2? Well, we factor. So I'm going to go ahead and get everything on one side so it's equal to 0 so I can solve. So move that 3 secant of x over to the other side. And now we're going to factor. There's no GCF, so it goes right to two binomials. Only one option to get secant squared. It has to be secant of x times secant of x. Last term, it's a plus 2. If the last term is a positive, what do you know about your signs then in each of the binomials? Well, they have to be the same. And how do you know if they're both plus or both minus? Look at the middle term. It's a negative. That means both of my terms here would have to be negative to add to a negative. Now, I love prime numbers. The last number is a 2. There's only one option that multiplies to a 2. It's 1 times 2. Double check and make sure that that works. So outsides you get -2. Insides you get -1. So I'm doing that product and that product. Double checking to make sure I get that -3. There was only one possibility, though. So that's the only thing that could work. All right, so we can set them equal to 0 and solve. All right, so we have secant of x equals 2, and we have secant of x equals 1. All right, now again, these are secant statements, so I don't memorize secants because I know I can rewrite them as their reciprocal sentence. So what's the reciprocal of secant called? Well, that's cosine. So I'm going to rewrite this first one. So if secant of x equals 1, cosine of x would be the reciprocal of 1, which is still 1. Secant of x equals 2, the reciprocal sentence would be cosine of x equals 1 over 2. So we'll talk about what these triangles look like then. So first one, when is cosine equal to 1? Well, that's definitely a special value, something that we can do. When is cosine equal to 1? Well, that's at 0 degrees. And again, this is all values, so I'd say plus 360k. And again, if you don't want to be redundant, you can just say 360k because 0 is an integer. Your other one, when is cosine equal to a half? Adjacent over hypotenuse, totally legitimate triangle there. That would be at 60 degrees. Plus 360k. Again, it's all possible. And is cosine 1/2 anywhere else? Well, cosine is positive in quadrant 1 and also in quadrant 4. So that means I also need to think about the 60-degree reference angle down there. So that would be 300. So you really have to get in the habit of thinking about those other locations. But when I say all values, the only difference really is that, yeah, it's all the coterminals too. All right, what we're going to finish up with for this part 2 is a couple where we're talking about principal values. So we need to remember back to chapter 6 here, what we mean by principal values. So we had some restrictions that we had to think about. Now, the nice thing about it is that when you solve then, you only have one solution. It's only that principal value, just kind of like a square root, the principal root. We only have to worry about one, but you have to remember what the restrictions are. So if you notice I use capital letters here, the restriction for cosine was 0 to 180, or 0 to pi. For sine, it's -90 to 90, so quadrants 1 and 4. And then tangent is the same, it's just parentheses, meaning not included, because remember the graph for tangent is undefined at 90 and negative 90. So when you say your solutions, you have to maintain that interval. You have to be somewhere in that range of values. Okay, so let's take a look. We're going to still solve the same then, though. Again, it's just how we write our answers that it's different depending on what our domain is. So let's take a look at the first one. It says tangent of x minus square root of 3 equals 0. Now, when I say check your functions and your angles, there's only one to check. There's only a single variable there. It's just tangent of x. So I don't need to substitute because it's a single variable. And what degree is it? That's degree 1. Fantastic. I love degree 1. We know how to solve degree 1. You just solve for it. Just do opposite operations. So I would add square root of 3 to each side. So I get tangent of x equals square root of 3, and I can just solve. So when is tangent square root of 3 for what angle measurement? Well, that's 60 degrees. Now here's the cool thing about principal values. 60 degrees is in my interval, negative 90 to 90. I'm done. I don't have to worry about anything else. I just need that one principal most important value. So that's why people like this. You don't have to think about, oh gosh, where else is tangent positive? What other angle would that be? We're set. All right, let's try the last one with principal values again. So principal values only, so single answers for each factor. Now take a look and ask yourself those questions once again. Are your function names the same? Indeed they are, they're both sine. Are the angles the same? Nope. Totally different. 2x and x, those are different values. So what that leads me to believe is I'm probably going to have to substitute. My angles are not the same. That's kind of a dead giveaway. So I'm going to have to substitute. Now when you look at the things you have choice over, sine of x, not much you can do there. 1 over cosecant. I would much rather deal with that. Now here's a great deal with this one. Sine of 2x, look on your formula sheet. Find it, double angle. There's only one option. You can't screw this up. There's only one thing you can do. There's only one substitution you can make for sine of double angle, and it's 2 sine of x cosine of x. That's it. It's not like cosine where you have to choose. This one is sine. There's only one. Now, check out your angles. You've accomplished your goal. All of your angles are the same, but now we have another function. Now we have cosine as well. So we made one thing a little bit better, maybe that one a little bit not so nice. I'm going to rewrite this as an algebra thing. I want you to take a look at it, what I just wrote in red. So again, everything's in sine and cosine. Those are not like terms. I'm kind of stuck. Look at it as an algebra thing. What could you do? Well, there's a GCF, right? There's a common factor, so we're going to pull that out. So all of those strategies we've talked about, if you get stuck, rewrite it as an algebra thing, you might be able to see then, oh yeah, I can pull out a sine of x. And then I can take each of those factors and set them equal to 0 and solve. So I know the factors don't have the same variables in there. I know one's a sine and one's a cosine. It's okay. There's two unique factors. They're separate. You just set them equal to 0 and solve. All right, so when is sine equal to 0? Principal values, that would be when x is 0. And when is cosine a half? That's when x is 60. And again, it's principal values. I only need that one value in the domain of the function. So we've talked about a lot of strategies in terms of algebra. Look for the degree of your function. Rewrite it with x's and y's. Look for GCFs. If it's degree 2, factor it. Break it down into binomials. If it's degree 1, just solve for it. But if the angles and functions aren't the same, you got to look for a substitution to make that happen.